So the mesolimbic dopamine pathway is also implicated as a role for addictions. So how it works is here we're kind of talking more about the mesocortical limbic dopamine system. So again, that kind of accesses or sends information to slightly different areas than just the mesolimbic pathway that's implicated in schizophrenia. So here what happens is we have the VTA. Now we're going to pretend that these three colored neurons here are all within the VTA. Definitely not to scale, but these three neurons would be within the VTA. So the VTA is the origin of the mesocortical limbic system and is composed of our dopamine projection neurons. So those would be the red neurons in this picture. And they're under inhibitory control of GABAergic interneurons. So the green neurons are interneurons within the VTA that are GABA neurons. So sometimes this will be described as an independent nucleus at the tail of the VTA. So you might hear people talk about the rostromedial tegmentum. So that's within the VTA, but for this class, we're just going to call it or talk about the VTA in general. Okay? So this is the areas. Now, the main targets of the dopamine neurons is the nucleus accumbens and the medial prefrontal cortex. Now, what addictive drugs do is they cause an increase in our mesocortical limbic dopamine. So it increases the amount of dopamine that's sent to the nucleus accumbens and the medial prefrontal cortex through three distinct cellular mechanisms. Okay, so for those three mechanisms, we're going to focus on this close-up picture. So first, let's just go over what happens naturally. We've got our GABA interneuron that sends an inhibitory projection to our dopamine neuron. Okay, so our dopamine neuron, then down here, these would be the dendrites. So the dendrites are receiving inhibitory information from our GABA interneuron. We've got our cell soma, and then we're sending dopamine axons and axon terminal buttons to our nucleus accumbens medial prefrontal area. Okay, so those are, we've got our dendrites, soma, axon terminals. Okay, now there's three areas where drugs can act, which will cause this addictive increase of dopamine that's sent. So again, normally the GABA neurons would inhibit the dopamine neuron from sending dopamine out. So there's what the drugs are going to do is they're going to increase the amount of dopamine. Now the first place it can act is on that GABA interneuron itself. So drugs like opioids, cannabinoids, and benzodiazepines will actually inhibit the inhibitory neuron. Therefore, by inhibiting our GABA neuron, then what we're going to get is that the dopamine neuron is no longer being inhibited. So it's now allowed to act and send its dopamine out to its areas. Okay, so that's the first one. So this is what we call indirect disinhibition. Now the second type of activation of the dopamine neuron we can get would be direct activation of the dopamine neuron. Now the best example of that is nicotine. So what nicotine will do is it actually stimulates, or it sends an excitatory, it provides an excitatory reaction on the dopamine neuron itself. Okay, so it will usually on the soma there will be some receptors here that nicotine can bind to and excite the dopamine neuron. So because it's acting after it's already been inhibited, then it then activates the cell, so now it can go on and send out dopamine. Okay, so we've got indirect disinhibition on the GABA neuron. We've got direct activation in the soma via nicotine. And then the last one that we have would be interference with dopamine reuptake. Okay, so that would be looking at cocaine, ecstasy, and amphetamines. What they do is they act on the axon terminals as well as in the dendrites themselves, where dopamine can be released. And what they do is they prevent reuptake of dopamine. So it makes the dopamine stay in the synaptic cleft longer, therefore creating more effect of the dopamine. Okay, so opioids, cannabinoids, and benzodiazepines are indirect disinhibition. Nicotine is direct activation, and cocaine, ecstasy, and amphetamines would be interference with dopamine reuptake. So note that the latter group are dopamine interference with the dopamine reuptake also will increase the dopamine in the VTA itself. So when it blocks the reuptake in the dendrites, then it's also increasing dopamine within the VTA. And this, what it does is it's owning to the perturbation of the reuptake of the dendritically released dopamine. So we don't get the dopamine coming back in the cell here, so we can actually possibly activate other dopamine neurons within the VTA itself. So now we know where addictive drugs act and how they can act in 3 different ways to increase the amount of dopamine. But how does this relate to addictive behavior? So addictive behavior has been linked to impulsive traits in humans. So people that tend to exhibit what we call impulsive traits, so that could be antisocial personality disorders or ADHD, those are what we characterize as impulsive traits. We actually see high correlation in those patients who also then develop some kind of addiction. So impulse control is a manifestation of inhibitory control. So if you have poor inhibitory control, you're going to have poor impulse control because you're not going to have that natural inhibition that others have. So this is a component of executive function. This involves structures such as the anterior cingulate, the dorsolateral prefrontal cortex, the lateral orbital prefrontal cortex, and the motor premotor cortex. If you think about what all these areas have to do, you can see how inhibition of some of these areas are very important. If you don't have good inhibition of, say, the motor premotor cortex, then you're going to see patients that have a lot of maybe kind of tics, can't stop shaking their leg, they have that repetitive movement going on because they don't have that impulse control, they don't have that inhibitory control. So this control can be considered a gating event. So it has to do with the gating in the neurons. So how did we kind of figure out that impulse control or impulsive traits are correlated with addictive behavior? We have one really big example that I'm going to explain in detail. Yes, you'll need to know this experiment for the exams. But this is how we can see the correlation between impulsivity and then later how that can lead to addiction. So in this experiment, then we first started by measuring impulsivity in rats. So rats were trained to nose poke to receive a reward. So pretty much there would be a screen, like a touch screen, or a physical button on an apparatus, and then in front of the screen would be a infrared beam, and every time they poked the screen, the beam would break on the apparatus, indicating that the rat poked. They did a nose poke. So that's how we measure nose pokes. And so the rats were first trained to just do a nose poke and receive the reward. After they were trained to do that, then a time delay was then introduced so that repeated nose pokes will only result in food reward if the rat waits the appropriate time. So for instance, you can only poke once every minute. If there was a premature beam break, so if the rat poked the screen twice in 1 minute, something like that, then the time interval would be reset and the reward would be withheld until the appropriate delay had lapsed. So this is a slight punitive effect. So the rats were trained to only poke after so much time. Rats were then sorted into low and high impulsivity groups based on how well they were able to not break the beam prematurely. So rats that repeatedly nose poked without observing the time trial would be placed in a high impulsivity group. They weren't able to hold themselves back from poking their nose. Those that were able to do the task correctly and wait would be a low impulsivity group. So they had low impulsivity. Okay. We then took the rats and measured them for addictive behaviors and dopamine binding capacity. And what we found was that the impulsive rats had significantly higher levels of cocaine self-administration and significantly reduced dopamine receptor availability in key brain regions. So here are some of the results from that study I just talked about. So our impulsive rats would be the solid black dots, and the low impulsive rats would be the open dots. So what we see here is that on baseline, we have baseline day down here, and then here percent premature response, so that's premature nose poking. The low impulsivity rats had less premature responding than the impulsive rats, so that's how they were categorized. And then we have choice accuracy, so it didn't matter if they were low or high impulsivity, they were still able to correctly choose things. But then when we look over here on the right, then we have the amount of cocaine self-administration. So how we measured if a rat had an addictive personality or would become addicted easily to cocaine, was the rats now, when they pressed a lever, it would give them cocaine, so they could give themselves as much or as little cocaine as they wanted. And what we see is that our control group, the low impulse rats, they did give themselves cocaine, but they didn't give themselves nearly as much cocaine as the impulsive rats. And even as the number of sessions went on, so as time went on, the low impulse group kind of stayed around the same amount of cocaine, whereas the high impulse group continued to grow the amount of cocaine that they self-administer. Now, if we look at a PET imaging of the dopamine receptors, so the amount of D2, D3 receptor agonist in these rats, then it showed that the high impulsive rats had reduced binding potential in the ventral striatum. Okay, and so that's what we see down here. We have the low group and the high group. So we see reduced binding. The average here is lower in our high group than in the low group. So they have less of the less receptors in the ventral striatum. And we know that because there was less antagonist bound in that area. So how we did this was, it was kind of like immunohistochemistry, but instead of using an antibody, then we use an antagonist that will bind to the receptors, and then we can quantify the amount of receptor or of antagonist at the receptors to then quantify the number of receptors. Okay, so if there's less antagonists, then that means that there's less receptors, because there's less area for the antagonist to bind to. So that's how we know that there's less receptor availability in our high impulsivity group as compared to a low impulsivity group. Okay, so reduced D2, D3 binding potential is correlated with our high impulsivity and addictive behavior when looking at cocaine self-administration. Now, we don't see much of a difference here in the dorsal striatum, but we do in the ventral striatum. Now, how does addictions and schizophrenia kind of connect? Because we know that dopamine plays a role in both of these, especially the mesolimbic pathways. So we see that actually a lot of schizophrenic patients also experience addictions. So there's a very high comorbidity in schizophrenic patients and addiction. So it's estimated to be about 75% of schizophrenic patients also experience nicotine abuse, and about 50% of schizophrenic patients experience alcohol or drug abuse. Other than nicotine. Substance abuse can be a precipitating event in schizophrenia, so some patients experience addiction before they exhibit the first stages of schizophrenia. So cannabis or amphetamine intoxication is a frequent precipitant for the first episodes of psychosis. So it's not saying that substance abuse causes schizophrenia, but it may play a role in aiding the first episode to occur earlier, perhaps. A lot more research needs to be done, but also substance abuse of cannabis is, a lot of that's done with early substance abuse, like in teenagers and stuff. When schizophrenic onset is in the teen, early 20 years. So the time where people tend to start using schizophrenia is also about the same time patients started exhibiting their first episodes of schizophrenia. So perhaps it's just a coincidence. So again, a lot of work is now being done to study more this relationship between substance abuse and schizophrenia and as a precipitating event. So that's it for dopamine, guys. Again, there's a summary slide on your notes. On Friday, then we will cover noradrenaline or norepinephrine, which will be the last of the catecholamines that we're going to talk about. And then next week we will cover serotonin.